Okay, let's start. So Dan won't be here today. He's traveling. So I'll be presenting today's lecture. You can hear me in the back? There? Okay, I will speak louder. Okay, so the homework 4 is going to be released next week. So you're going to have a little break this week. And midterm is close. In almost 3 weeks, we will have our midterm. Midterm is going to be on paper. So you need to be prepared to be asked about anything which is presented in the class, especially on the slides. So try to go over the slides and understand everything that you have seen as slides. The questions are going to be either directly about the concepts we have learned or some sort of their perturbation. So if you understand the slides well, and if you have a good understanding of what's going on, you should be able to solve all of these perturbations. And any questions before we move on? If you have any questions about last lecture, yeah.
Do you know the format of the midterm?
It's all other.
Do you know the format of the midterm?
By format, you mean?
Like, is it like a multiple choice, or is it short answer, essays?
Mostly it's going to be long answers. So you will be asked about, like, show that this works. It might have multiple parts to guide you to the answer, like first show this, then show this, show that. There might be some short answer questions too, but it's mostly going to be long. And we have the projects for proposals deadline in 15th, almost 8 days from today. If you haven't started yet, try to start it. Think about it. There are a lot of interesting things that you can do about machine learning. So you have lots of freedom. If you haven't formed a project, try to talk to people. By show of hands, how many of you don't have a group yet?
Do we have to have a group, or can we do individual?
Adam, I think they need to do individual. They can do individual, right? Yeah, at least 2.
You can do individual projects. If you haven't found a partner, feel free to post a note about it on Piazza.
Yeah, or can you again, by show of hands, who doesn't have partner? So look at each other. Find people, right? So after this class, talk to each other. So that's about the projects. And today's lecture is going to be about neural networks. I'm sure almost all of you have heard about neural networks because a lot of the topics related to neural networks are hot. So if you know about neural networks and if you can do interesting stuff with neural networks, you are probably going to be hot in the job market. So it's a very interesting topic. So why neural networks? Just like anything that we learn in this class, neural networks are also a method for approximating a mapping from input space to output. But it has very cool properties. It is relatively robust. So for a lot of problems, irrespective of whether your input space is continuous, discrete, and how the output space is, these methods that we are going to study, neural networks, they're relatively robust. So you can essentially use it on a very diverse set of input-output spaces, but the problem is that the models that we are going to create, they are relatively complicated, and it's going to be hard to learn them. But we are going to introduce one relatively old algorithm that people have been using still so far. They're still using it. Backpropagation, which is a relatively efficient way of learning these networks, right? To be a little more formal, it is a mapping from input space X. It can be continuous or discrete, and it maps it to another output space, which can be, again, discrete or continuous, right? And as I mentioned, it is an approximation of reality, which we don't know. And the reality can be arbitrarily complex. So we need something which is relatively flexible to so that we can approximate the underlying reality. The algorithm that we are going to introduce here, as I mentioned, is the backpropagation, which we are going to introduce for learning a structure like this. So we are going to first start with something called a multi-layer neural network or multi-layer perceptron. And this structure is introduced around like 50 years ago, but still it is a very popular structure. You have seen this structure in the previous lectures. Let me just remind you what this is. So we have input. The input is the first layer. And we pass, after passing this input to our network, this input layer is connected to some hidden layers via some weightings, right? And we might have multiple hidden layers here, and each layer passes its output to another hidden layer until in the last step we have this output layer, right? So we are going to give the way we are going to use it is like this. So we are going to pass an input to this, and it's going to give us an output, and we are just going to use the output. So this is how we use it. The training question is, given a pair of inputs and outputs, how we can tune the weights of this function so that it works in desirable way. And desirable way is minimizing some sort of error function. And why we in the first place, why did we come up with this kind of system? The whole motivation was that, you know what, all of these biological systems, we see them in nature, they're perfect, they're working, they're awesome. So we somehow, maybe the right way of solving AI and machine learning is trying to imitate what we have in nature, right? So people started thinking about mind, which is one of the most amazing systems we have in nature. And they thought, okay, so we have lots of neurons in mind. So we have like 10 to the power of 10 neurons connected to each other in a very complicated way in mind. Why not we create a structure which imitates this in some ways, right? And the reason that this system in our mind is working is not because neurons are fast. It's mostly because this huge number of neurons, they are working in a massively parallel fashion. So each neuron is independent of other neurons. They're just working and passing outputs to each other. And somehow this composition of billions of functions, much more than billions, this gives us this intelligent behavior. So we thought, okay, maybe we can create a system which acts like that. And another interesting thing about this biological structure is that this representation of facts and reality is distributed among a small information inside these neurons. Somehow these small information inside neurons, they get combined to each other and they create very abstract notions in our mind. But really, there is a huge distance from this biological argument to what we have in reality. So essentially, we can make if we create like a computational unit which imitates a neuron, it can be arbitrarily fast, but we are going to have lots of problems in simulating that. First of all, in reality, mind has lots of neurons. We don't have enough infrastructure, computational infrastructure for simulating that. And if we really open the brain, the neurons are really small. It's just their power is coming from their complicated connections to each other, which so far what we have in reality in computational world is fast neurons, but with less computational units, which is very, very different from what we have in our mind. So if someone tells that neural networks is the right direction because they imitate the reality, the nature, that's probably wrong because they're very different. But that was the main motivation. So okay, let's see. Okay, let's see how we can start imitating this neural structure in our mind. So the first idea that might come to someone's mind for simulating this neural network is maybe I can. Okay, so the first step designing the small units in our neural network. So the first step is to decide what are each of these green or blue dots. They're blue, but you see them, I think, black. These blue dots here. So we need to see, okay, how we can design these. One idea can be using linear units. We can put linear units. If you remember, we had we had lots of examples of these linear units. So basically, you get some vector of inputs, right? And you dot product them with a weight vector, and we call that a linear unit. We can put linear units here, but remember, one big motivation was that we want to get a relatively nonlinear behavior from composition of these units. If you just compose linear units, it's not going to give us a nonlinear behavior. So somehow we need to add a nonlinear step here. Some observation that scientists have made about neurons is that a lot of these neurons in our mind, they fire or they create output when the input to these neurons, which can be some sort of electricity or some sort of signal, if this input is when it's more than a threshold, these neurons fire. Okay, so how can we simulate this behavior? One way of simulating that is we can put a threshold function in the output of weighted average of the inputs, right? So basically, we get a set of inputs, we multiply by some weights, we sum them, and we give the result to threshold. If it is above some threshold, we can output some value. It's basically the same thing here. We find the dot product of input and weight. We subtract a bias term, and we find the sign value. The sign value can be 0 or 1, let's say. Okay, but this is actually nice because this is compatible with what we have in nature. But the problem is that gradients are nice for doing optimization, and this function, which has this step here, it's impossible to find this gradient. That's why we are kind of hesitant to use this. So we are going to, instead of this, we are going to use a kind of a smooth approximation of this function. So we are going to do this. So we have this set of inputs, the vector of inputs. We are going to weight them by some w's, w1 to w6. We have x1 to x6. And each of these are connected to another unit. Let's call that x7. xij connects node I to node j. So this is w1 to 7, w6 to 7. We sum them, and we give the resulting thing to a function of form 1 over e to the negative x, and we get the output. The output is ours. A question: what is the range of output at this stage? To 1. So it is essentially an approximation of 0, 1 system that we have previously. So we are smoothing the output space, and it is differentiable. So it's going to be easy to optimize over this function. And this is essentially this representation here. This nowadays people usually call this a logistic regression. And people use this for classification, although it's called regression, because the output is in the space of 0 1 space. You can treat the output as like probability of something being true or not being true. So again, to be a little more formal, let's define this variable net j, which is the value of the this linear combination of x and w's in node j, and we are going to pass this net variable to a sigmoid function, and the output of this sigmoid function is going to be our output, right? And tj is a bias term. So tj is a bias term that we are going to use again as an additional degree of freedom for tuning our system.
So it's a constant?
It's like the bias term that we had in, like, you remember we had linear model. We used to add a dummy feature. Mm-hmm. So, okay, let's say this is our model and we want to train this. What are the parameters in this model? What are the unknown stuff? Yes, W's and T. And this might seem a little obvious and ridiculous to you, but some scientists, McClaw and Peet, they showed that this unit, a combination of these units, actually just this unit, they can simulate logical, they can have logical behavior. This might sound very ridiculous, but in fact, 60 years ago, it was a big deal. It was a big deal that these units can simulate logic, because the whole AI, when 6 years ago it started, everything was based on logic. Like, so, because logic really makes sense. We can really understand logic. It's easy to interpret. So that's why everyone, at first, they started doing everything based on like logical implications. But a few years later, and by a few years, I mean like 30 years later, they realized that logic might not be expressive enough for explaining all of the behaviors that we have in nature. That's why in today's machine learning we have more of a statistical models rather than logical models. So the claim is that this unit, this logistic regression, can simulate and, or, and not. Let's just think about it. So we have this unit that I introduced in the previous lecture, previous slide, and we want to use it to simulate and. So how can I design it? I want the output to be 1, or to be 1 whenever all of my inputs are 1. Any suggestion how I can set my weights so that it does the desired behavior?
So you can set all the weights to 1, threshold to be -n, and features.
Yes, exactly. So that works too. Let me say it a little more general. So just remember that this was our model. So we get a linear weighted sum of the inputs and put the output in a sigmoid function. Another way of saying his suggestion was, let's say I choose arbitrary threshold value, and I set all of my weights to be Tj over n. And whenever my inputs are all 1s, I'm going to see 1 in the output. This is a smooth function, but you can say if when it is above half, I can consider the output as 1. And I can use a similar trick to simulate or. So I can say, let's set all of my weights to be Tj. If one of them is at least Tj, the output is guaranteed to be above Tj, and that's why I'm going to get 1. And with a similar trick, you can simulate not. So whenever I get 1 in the input, the output should be 0. This is really big deal because essentially it proved that neural networks can simulate any arbitrary 0-1 logical function, because you can represent one logical function based on 2 layers of ands, and ors. And essentially, by this claim, you can simulate any logical function by 2 layers of these units stacked together.
So does this mean that neural networks are Turing complete?
To be honest, I don't have a good answer for that. But we can discuss that later, because it might be trickier than that. I don't have an answer. If anyone has a better answer. Okay, let's see how we can learn these models. Essentially, the way we are gonna start attacking this learning problem, we are gonna first start with the output layer, and we are gonna try to generalize this to multiple layers stacked together. So, in fact, if you think about it, learning just one layer is equivalent to learning all of the models that we had so far, like all of the online learning algorithms that you have learned so far, they can actually be applied for learning the output. But let me just remind you what we have had so far. And I'm going to basically introduce a set of perturbed algorithms from the set of things that we have learned. So this whole the story of neural networks and their learning started from psychology community. So they started saying that, okay, so whatever the algorithm is, or rational behavior is, it's going to be something like this. So whenever I make a mistake, I should change myself. So this guy who was a psychologist, he said, HIP, or HIP, he said that, okay, so I'm going to define this kind of update for learning my model. Whenever OI and OJ, they're compatible, one of them is reality, one of them is wrong, the prediction. If one of them is, if they're not compatible, I'm going to change my weights. Otherwise, I'm just going to do nothing, right? And this was mostly when he introduced these kind of notions. It wasn't really in a computational level. It was mostly like they were analyzing how this psychological behavior changes, and it took a while until these people in computational sciences they took these notions and they applied them in a practical way. Rosenblatt said that, okay, so I'm going to do this. I'm going to get one input. I'm going to calculate update, and I'm going to create an additive error term. And using this additive update, I'm going to update my hypothesis. And this is something that nowadays we call this a perceptron update. So I'm gonna have this linear function. Let's say this problem is linearly separable. I'm going to perturb this with additive updates so that it is compatible with my training data. And let's just review what we had. So this is what we have studied so far as perceptron updates. TJ is the target, and XI is the input that we see. OJ is what we predict as the prediction of model, and we are going to update our weight in this form using additive terms. And this update is, if the output is correct, we won't make any changes. If it is wrong, we are going to change it. If we need to increase the weight, if the weight is small, we have made a mistake. If the weight is small, we are going to increase it. And if the weight is big, we are going to decrease it. So this is the observation that we can make about this update rule. And this is the overall algorithm. So we initialize, we have a set of weights, right? So we are learning this model. We have, this is just one layer. We don't have the neural network yet. It's just one layer. Let's say this is the output space. We have one output, or it can be multiple output. We have a vector of inputs, and we have a set of W's, and we are learning the W's. So we are going to initialize all of the weights randomly, and we are going to go through the training data. We are going to first give the input, make prediction, compare the prediction with the output based on their difference. We are going to make an update to our weight, and next, again, we are going to move on to the next instance, and we are going to do this update until we have some, let's say, we have some stopping criterion. The question here is that, is this really going to converge or not? Essentially, you have seen most of these notions in previous lectures. I'm just reminding you. So this is going to converge if the data is linearly separable, right? But how long it's going to take, it doesn't tell us anything, right? That needs more theory. We had some analysis for, like, based on mistake one and things like that. And when the data is not linearly separable, it might actually cycle. So we might go through the data, we might update. It might never. It's possible that it's never going to converge. And one important issue here is the issue of representation. So I remember that when I started lecture, I said that we need a relatively complex structure for simulating the behaviors that we have in nature, because nature is complicated, and for simulating that, we need something which is relatively flexible to simulate the nature. And this behavior, that's why neural networks are desirable. So when people started thinking about this perceptrons, or just one unit of a neural network, the first step was to analyze the representation behavior of this perceptron. Minsky and his student, Papert, or I don't know how to pronounce his name, they wrote a very nice book in 1969 about perceptron. Actually, the name was Perceptron. And they demonstrated some interesting behaviors about perceptron and its let's say it's about training it, about its representation, and they showed some negative issues about representation properties of perceptron, which resulted in basically, okay, so basically they showed some results, for example, like perceptron cannot represent relatively complicated functions like parity function, which is something like XOR. And or something, a more interesting example is, let's say you are doing some sort of image classification, and the task is to classify, let's say, decide whether this fingerprint is correct or not. If you don't do a good job in feature engineering, these models they will be sensitive to rotations. So they're not really, inherently, they're not complex enough to capture symmetry or these kind of behaviors. So these kind of negative results about representation behavior of perceptron resulted in decline in interest in perceptrons and, as a result, neural networks, which later people nowadays, they call AI winter. There was a huge cut in AI's fundings after these observations. But later on, people realized that it's actually not that. If we stack them, we can actually approximate. If we have a neural network of 3 layers, we can actually approximate any function with any property. Let's move on to let's try to formalize how we found these updates based on by doing optimization over a function which shows error. So let's define this error. What is this error? What does it mean? So we have the summation over all of our data, over all of our training data. The target, TD, is something that I have in my data. And OD is the prediction that my model makes given an input, right? So this basically says that how much my output, my prediction is different from my target. And I sum them, and this becomes my error given the parameters of this model. And I know that the prediction, let's for now assume that my output is basically a linear model. And if we want to, we know that one way of finding the parameters of this model is doing gradient descent. I can essentially, at each step, I can find the gradient with respect to my parameters and go in the direction of gradients until I find the minimum point, and that's going to be my optimal point, right? So essentially, we find the gradients with respect to each parameter, and I update each W with the gradients, right? A negative direction of gradients with some weighting which shows my step size. And let's actually do this together because we are going to reuse this multiple times during when we are deriving the backpropagation algorithm. So this is my error term. I sum over all of my data set. I'm gonna find derivative with respect to one element of my weight vector. Let's call that Wi. This is my gradient with respect to Wi. I can take this gradient inside the summation, and this is quadratic function. I can put there's 2 missing here. So it's going to be the function itself times the gradient of whatever thing we have here. And OD is, let's say, for now, it's a linear function. And the gradient of this linear function is going to be xid, where xid is the ith term in the xd vector. Right? So this is going to be our gradient. And given this gradient, now I can do gradient descent updates over this linear model. Right? So this is going to become my model. So this is the gradient that I calculate, and this is I multiply this by step size, And at each step, I'm going to calculate my output. And given these outputs, I can calculate my gradient, my update rules. And I'm going to update my W's by adding these. Right? And this is going to be my updates. And this is guaranteed to converge because my error function, as I showed you in the previous lecture, this slide, this is a convex function. I'm guaranteed to find the correct answer by doing finite number of updates. I can simplify this. I can say instead of doing this, instead of finding this sum of gradients over all of my training data, I'm going to do this instance by instance. So instead of having the sum here, I'm going to remove it. And I'm going to say I'm also going to have this outer loop over the instances. And whenever I see an instance, I make a prediction. I find this update rule. I'm going to apply this update rule right away after seeing the instance. This setting we call incremental update. Right? This in practical settings, this is usually faster, but there is no theoretical guarantee in its convergence. Only for a few cases, we can just say that this is going to converge, but this, we don't know when, you know. And this might not converge to the global mean. This is going to converge to something, but not necessarily the global minimum. So far what we had was this. So we have this neural network. We said, okay, so I'm going to ignore the hidden layers. I'm going to assume that I have only the output space, the output layer. It's just one layer. And I can learn it with lots of algorithms that I had so far. So we had multiplicative algorithms. We had additive algorithms for learning this. I can use them in a batch way, basically calculating my updates over all of my training data, updating once. Or I can update my model incrementally. So I see an instance, update my model. I see another instance, update model, incremental. And now we know how we can learn this output layer. And next, we are going to see how we can generalize this for our hidden layers. So now we have, again, to remind you, we have this structure, the input, hidden layer, and output. Making prediction with this model is easy. So can someone, again, just remind all of us, how we can make prediction with this? Let's say my weights are fixed, or the parameters are known. I see an input. What is the procedure for making prediction? Louder.
We have a threshold and see the output is above the threshold. Make different labels to the.
Let me rephrase this. So we see a vector of inputs, and these edges, they represent weights. I multiply by I multiply this value by all of its weights. I pass it to the units in the other layer. I do the same thing for this value too. I multiply by its weights. I pass the values to each of these units. I do this for all of these units. Now I have values for each of these units. Now I multiply this value by these weights, do the same thing for these weights, do the same thing for this. Now I have values in this. So making evaluation in this system is very easy. But the question is, how can I update this, right? Now, but the only thing that I know is that I can evaluate my error terms in the output layer, right? Because I have my prediction, I have my target. I can just find it. Let's say I can find the difference, and that's going to be my error. The question is, how can I bring these error terms to these weights? By the way, one side question. Here, my output is. I have two outputs. Why having two outputs might be useful for any application? I mean, let's
use it for multi-class classification, right? Where each one represents the probability that the class you use take the maximum as your class.
Right. So he's saying that, okay, so each of these units in the output space, they're binary. I can do multi-class classification. Let's say I have 10 classes, and I want to see whether given input, this instance belongs to which of these 10 classes. I can design a neural network with 10 outputs, and the output which gives me the biggest number, I'm going to say, oh, this instance belongs to that class. Right? So this is one way of doing multi-class classification, but it's not the only way, but it's a good way of doing that. Okay, again, I know that I can find error here. I know that I can train these weights efficiently by finding the gradients of this update and updating these weights here. What I'm going to do this is maybe something like this. If I have a differentiable function here in each of these units, I can get these error terms and update each of these weights too. So that's going to be my solution. So these are, so I'm just going to read this. If the activation functions are differentiable, then output of the network is also a differentiable function of the input and weights in the network, right? So, an activation function is essentially referring to the sigmoid function that I have in the output of linear summation over inputs here. So I'm going to define error function here, find the gradient, and find the terms for updating all of the weights in the hidden layer. So let's be a little more formal. So I have this network. I have output 1 to output k. So I have k outputs, right? And I'm going to define this error as the error over all of the instances and all of the outputs. So I have the summation here, k, over all of the outputs, variables. And this summation, the sum is over all of my training data. I want to minimize this, but since this summation over all of the training data is going to be a little computationally hard, or it's going to make my life harder, I'm going to drop that, and instead of minimizing error over all of my data, I'm going to do my updates incrementally. So given one training data, I'm going to minimize that error summed over all of the outputs. And this is basically how I'm going to make updates. So I'm going to find gradients, this error, with respect to each of my W's, and I'm going to update that weight with this term. So remember, this is our model. We get X values, we weight them by W's, sum them, give the output to a sigmoid, minus the threshold value. This becomes our O, right? So as I mentioned, we are going to do our updates incrementally. So I find the error, I write the error over given a training instance. And I find the error over all of my output variables. And this is what I want to find. So the error with respect to each of these W's in the output space, right? But instead of finding these error terms with respect to each of W's, I'm gonna use the tricks from linear algebra and real analysis. Basically, because this W has its effect via this net J, instead of finding the direct derivative with respect to W, I'm going to first find the derivative with respect to net J and find the derivative of net J with respect to W. It's basically the same one algebraic group, right? So we have this unit, fix this unit I, fix this unit J. The weight connecting these two is Wij. I'm going to find the derivative like this. And in fact, I'm going to do it another time. I'm going to find the derivative of error with respect to O, because in the output, I know the prediction of my model. This O is calculated given net J. So I give the net J to my sigmoid function, and I get O. And net J is calculated by linear sum of inputs weighted by some input. And the resulting thing is going to be this, but let's see how we calculated this. So this Tj minus Oj, this corresponds to this term here. Why? Because this error was defined in this form. If you find the derivative with respect to some Oj, we will drop the sigma, and only the term which corresponds to OJ, the jth index of that is going to remain. This term corresponds to a sigmoid function. So this is how OJ is calculated based on net j. If I find the derivative, I will have this. And similarly, net j is calculated by weighting my inputs and average and finding their summation. This is my gradient. So what do we have so far? So we have two units. One is output. One is one hidden unit here. The weight between them is wij. I give xij to this unit. This is my gradient times a step size. Let's define a parameter called delta j. The reason that we define these parameters, delta j's, is because we are going to reuse this inside our algorithm and create a very nice looking algorithm based on just these deltas. So you will see another. So basically, you should just remember this. So the update is r delta j xij. So that's the only thing. What is delta? We can look it up somewhere. It doesn't really matter. We have some delta. So delta represents the error. Now let's move on to the derivation of error for a hidden layer. So we have this unit here, I, another hidden unit here, j, and we have this output here, let's say O of k, right? What I want is the derivative of my error with respect to this weight connecting node I and node j, right? So I'm going to do a similar trick. I'm going to say that I can find, instead of finding directly with respect to W, I can first find the error with respect to the linear summation of the predictions in this unit, net j, and find its gradient with respect to wij. And I can use that argument again and say that, you know what, this error that I have in the output, that only what that error sees is a set of predictions, set of linear summations which are given to these outputs, right? So the effect of making decision using this weight gets transferred to these edges here. I can basically say that, okay, rather than finding this, I'm gonna sum over all of the edges connected to this node j, right? And I'm gonna again add an additional chain to this gradient, and this is essentially oh, there is a typo here. Okay, so this additional term is basically the output of, this is the gradient of net k with respect to wij. This is a mistake here. And this term should be familiar to you. This is something that we calculated in the previous step. This is the gradient with respect to this term that we have here. So basically, I can use the same delta that I introduced in the previous lecture for updating the output layer, and I can write my gradients in this step based on that delta. I can further continue the simplification based on this term. I need to simplify this. I still don't know what's this. And for this, I can, again, this is just algebra. I'm not doing something complicated. I'm gonna do chain rule for finding the gradients, and I'm gonna expand this as two gradients, and I'm gonna simplify in this way. Remember that this net k was the linear sum of a set of inputs given to it with some weights. If I find the gradient with respect to one of the inputs, what's going to remain is the weight corresponding to this input. And this gradient is basically the gradient. This OJ is basically a sigmoid function given this net j. And the gradient of a sigmoid function is this value. So what do we have so far? So gradient of what I calculated so far is gradient of my output space, my output error, with respect to one arbitrary wij in this layer, in this hidden layer. And interestingly, this error has this error term from the output space, output layer. So this is how I'm going to update this weight wij, the weight connecting node I and node j. And the delta, I define this term here to be my delta in this unit. And this delta has some error terms from the layer after that. So this is the moment that this is the aha moment. So I can write my error, which is delta j, in this layer, as a function of error term in the next layer. So, and this is irrespective of in what layer of network I am. So basically, I can do something like this. I can, at each step, I know how to calculate the errors in the output space. Now I found a way to calculate the error of errors in a hidden layer based on their errors in the next layer. I can repeat this many times until I have the error terms for all of my layers. So that's going to be that is the backpropagation algorithm. So I'm going to have this loop, outer loop, over all of the instances. I know I can calculate the errors, the deltas, in the output layer. This is my update. Given this delta, for any of my hidden layers, I can calculate the deltas for the previous hidden layers based on the deltas in the layer after that. And I'm going to do this until I have these deltas for all of my hidden layers. And using these deltas, I'm going to update my W's based on its corresponding delta term. And this is essentially, people call it delta rule. So everything is nicely represented as deltas. So let's just show how things are so far. So I get one input. I have these hidden layers, this, right? This is an example network. I get input. I make predictions based on these weights here. I have the values here. I make prediction. I have the values here. I make prediction based on these W's, and I do this until I have values here. I know the target. Let's say I want to train. I find the error term here. I have a delta here. I have a delta for each of. I have delta here. I have a delta here. I'm gonna use the deltas to update my W's here. Given these deltas, I'm gonna calculate the deltas in this layer. I'm gonna use those deltas to update these, and I'm gonna use this, update these until I'm done with updating my network. I get another instance. I go here and I come back here. So that's why we have one forward step. We have this backward step. And this is the backpropagation algorithm that people, even after 30 years, people are still using it. It's very popular. A few comments about its behavior. We don't have guarantees on convergence. So before introducing backpropagation, I introduced another gradient descent algorithm in which I showed two scenarios, batch learning and incremental learning. And I mentioned that in incremental setting, I don't have any guarantees on global convergence. In some settings, I can say it's going to converge, but it's not guaranteed that it's going to converge to global minimum. But in the batch setting, I can make that guarantee. The same thing holds here. So because backpropagation goes over each instance by instance, I don't have any guarantees on global convergence of this. And usually in practical settings, it takes a very long time for this algorithm to converge. And people do lots of smart tricks for implementing this. People implement on GPUs and lots of fancy stuff. But essentially, the algorithm is the same thing. This is the algorithm. You can implement it in any way that you want. And you can define lots of ways for your termination. It can be the number of iterations, a threshold on your training, your error on the validation set, or lots of things. And you can, because, okay, so something that we need to be very careful when training neural networks is that we have this giant system which has lots of flexibility. If you add lots of units to this, it's going to have, essentially you are going to have redundant flexibility. It's going to be really flexible. And when you have very flexible system, it's going to be relatively easy for your training algorithm to overfit to your training data. So this is one tricky issue when we are designing a neural network. We don't have a very formalized way of choosing the structure of the network, and it is quite possible that you're going to choose a network which might be too big for your problem or too complex, and you might easily overfit your training data. So it's really important to make sure that when you're training a network, you're not overfitting. Or so sometimes it's just the trial and error. You choose something, see how it works, change the structure of the network, and train it and see how it works. And so these details are essentially the notes that you have seen so far. You have already seen in the previous lectures for how to properly train a machine learning system for a problem. Just like having too many units, which might result in overfitting, having too few units might also be problematic because your system might underfit. It might underfit your training data because it won't have enough flexibility in approximating your the correct solution for your problem. Something that people do sometimes, I'm not sure they're still doing, at least they were doing until 10 years ago, is sometimes it might be desirable to try to force your system to become sparse. Basically, try to force your system to use the least number of weights in neural networks. So this is going to be a problem. If you have if you have a huge network, having this sparsity properties is going to be desirable because it's going to try to force your network to use the least number of the weights, or at least use the weights which it needs. Otherwise, don't use it. So one way of doing that is adding priors on each of these weights. So people have come up with some sort of probabilistic models for neural networks by adding priors, which force this model to use small weights or zero weights. Another way of doing this is trying to add updates on W's so that at each step they get closer to zero, basically decaying updates to forcing the weights to become smaller and smaller. And they're going to get bigger only if they're necessary. Otherwise, they're going to get smaller and smaller. This is another trick people use. Another trick, a very small trick, which I'm going to briefly point to, is called dropout training. This is a relatively recent thing. It is an experimental observation. We don't have much theory on this, that why it works. We have theory on why it works for very special cases and simple structures. But in general, we don't have much theory that why this is interesting. So here's what the dropout technique is. So we have this neural network. It maps the input space to output space using a set of units. It can be 10 layers, it can be 1 layer. For now, let me just represent this with 1 layer, but the idea is the same for 10 layers. I'm going to do this. Whenever I'm at each step of my backpropagation, and remember, each step of backpropagation was observing one input, calculating the output, finding the error terms, and increment and adding and updating my weights based on the propagating back my error terms in the input weights. At each step of my gradient descent, my backpropagation, I'm gonna randomly drop or remove some of the units that I have in my neural network with some probability. So let's say I'm making a prediction, an input given to me. I'm gonna do coin tossing for each of the units. I'm going to go to the first unit, toss a coin. With some, if it's head, I'm going to remove it. If it's tail, I'm going to keep it. And I'm going to do this for all of the units until I remove some of the units and some of them are not removed. I still have them, right? And I'm going to do one update of one update of backpropagation. In the next step, assuming that nothing has removed, it's like when I say remove, it's not like removing forever, just for that iteration. I'm going to repeat the same thing for the next iteration, randomly remove, ignore some of the hidden units, make update, and go to the next instance. So basically, in each iteration, I randomly remove some of the units. I ignore them. So one cool observation is here. So these graphs, this is the error on my test data set. And so let's just ignore this. So let's say I'm training my model, and I'm tracing my error on my test data set. What do I expect to see? I have some arbitrary model. I'm tracing my error on the test data set. I'm not allowed to, but somehow I'm doing it. I'm cheating. What do I expect to see? Is it decreasing? Is it going up? I'm training a model, arbitrary model. It's not neural network. It can be anything. I'm training using trained data, but I'm looking at the error on the test data and other data. Is something random. Gonna drop.
I think so.
But we are training on trained data, but we are looking at the error on the on the test data. That's a good point. He's saying that because I'm training on the trained data, the test error is going to be higher. But my question is mostly about, is it going down or is it going up? Or how does it behave? Like, is it...
It's go down first and then go up.
Right, but that's a good point.
Once you start overfitting, the error on the test data is going to go up.
What is the role? Can you repeat?
Once you start overfitting on the trained data, then your test is going to behave worse than...
Right, so that is the answer that I was looking, and thank you. So he's saying that, okay, so this is the scenario. I'm training on the trained data. I'm looking at the test error. What I'm going to observe is, when I start my algorithm, the error on both of these train and test is going to decrease. Until, at some point, I'm going to start to overfit to my trained data, and that's the point that I'm starting to lose my generalization. I'm just starting to overly learn my train and just memorize it. And I'm starting to lose the generalization outside my trained data. And that's the time that the error on my test data set is going to start to increase. And we are actually seeing that behavior in some of these curves here. For example, here, I'm starting to decrease the error on the test data, and this goes up, similarly here, and similarly here, and similarly here. And this is the best way to stop our training. But since in practice we don't know, we are not allowed to look at our test data set, we don't see this, and we usually try to approximate this point with a validation set. Right? Something that Hinton said and showed empirically is that if you use dropout, if at each iteration of your iteration of backpropagation, if you remove some random units, what you're going to observe in the error in the test data is this. So the error goes down without hitting the overfitting point. And this is a very interesting observation. So what's going on here? Essentially, the way he tried to justify this was this. So he said, okay, so I have this network. For each of these units, I have two cases. They can be in the model, or I can just remove them, right? So let's say I have n units. For each of them, either can be in the model, or I can remove them, right? So the total combination of these, the total number of the different networks that I can have in this setting is 2 to the n. Each of them may or may not be in my system. So, and essentially what we are doing is that we are like trying to train on an average system. So basically we are trying to tune our system with this backpropagation and this random removal of the units in a way that it is robust to different configuration in the neural network, right? And another way of looking at this is regularizer. And the role of, if you remember, the role of regularizers in the model was to force the models to be general and simple and sparse, so that they're robust to different settings. And here we are basically applying that. We are trying to force our models to be robust by randomly dropping some of the units. We are saying that, okay, so what if you don't have this unit? What are you going to do? So train yourself in that setting. So this is going to give the network some sort of behavior averaged over all of these possible configurations for the system. And in fact, this idea of dropout, here we showed for hidden layer, but you can in fact do this in the input feature space. You can say, let's say I have a linear model. And instead of always training with this complete vector of inputs, vector of features, I'm going to randomly delete some of the input features, and I'm going to do updates with that. So in fact, using dropouts in real applications is really simple. It's just you randomly go through your parameters and drop some of them and train. It's the whole idea that all of the algorithms, they're the same. It's a trick. It's a very simple trick. A very small point before I finish. So Colin pointed out that we can use this. We can do multi-class classification using neural networks. That's a very smart technique. So basically, we say, so each of these outputs correspond to one of the classes, and and I'm going to choose the prediction to be. I'm going to say that this prediction belongs to one certain class if the output of that output unit is bigger than other units, right? That's one way of doing it. Someone might say that, okay, so I'm going to say that, okay, so each of these outputs are binary. And I'm going to say that for, let's say I'm doing M-class classification, I'm going to choose log M output units, and I'm basically representing the prediction and the output as a binary. So, for example, let's say I have 8 classes. For this, I can just have 3 output units, and assuming that each output is a binary value, I can simulate all of these output classes with those 3 units, right? So here the issue is that how I'm going to encode my output space in this way. Which one is better? That's another issue that we are going to discuss in maybe 3 or 4 lectures. Just a few small points. We showed that we can represent any Boolean function with neural networks with 2 layers. It's been proven that you can approximate any continuous bounded function with neural networks with 2 layers. This is a big deal. Any function which is continuous and bounded, you can approximate that function with a neural network with some weights. We don't know how to find that. That we don't know. We just know that you can do this. And if you have 3 layers, the theory is much stronger. It says you can approximate any function, right? One last point. The idea here is relatively different from stuff that I have explained so far, but it is very interesting. So here's the idea. So the idea is that when let's say I have this neural network, I have some training data, I learned this model. The idea is that these weights that I am learning these weights can also be interesting, might contain interesting information for some of the relevant problems that I might solve in future, right? So basically, the idea is that by training a neural network, I might directly learn some features or information which might be valuable for learning, for doing something else. For example, let's say I'm doing this. I have created a giant neural network, and what this neural network does is that is supposed to do is it's going to classify the images to whether they are cats or not cats, right? So I can gather a huge data set. I can train this model with images of some cats and some other images other than cats. And the claim is that I can later on reuse these weights that I have created for some other tasks. A perturbed way of thinking about this idea is this. So think about this. This is a neural network. This is not really neural network, but it looks like that. So the way it works is like this. I give an input. I calculate some values in the intermediate layer. And given the values in this intermediate layer, I do a reverse procedure, and I calculate some output values. The desirable behavior is when the input is very, very close to the output value. So the weights are unknown. What I know is pair of inputs and outputs. I'm going to tune my weights so that it's going to be relatively good in finding another output which is very similar to my input. Or I can rephrase in this way. Given two sets of inputs and outputs, it can tell me how close they are. This is basically the same idea. I'm going to find this W's, which tells me how input and output, how they are different. Right? So why this is important? So here's an example. Let's say this input and output, they are actually paraphrases. So I want to create a system which says, given a phrase and its paraphrase, which are very similar, I know that they're the same. I want to create this network which tells me when they're paraphrased and when they are not, right? And after learning this, so the resulting neural network is going to be something which, let's say, to some extent is able to tell me when sentences are paraphrased. And the hope is that after doing this, I'm going to get a set of vectors for my vocabulary, which are very informative about semantic information inside for each word. So this is basically an indirect way of creating features for some other tasks. So I can train a model on this paraphrase task. I can get vectors for each vocabulary that I have used in this paraphrasing. I can use it for some another task, let's say for question answering. So the whole point of saying this was that neural networks can be used for generating features for some other tasks. And this is interesting because one claim is that reality is complex, and doing feature engineering is a very important step of machine learning problems. And in some cases, who knows, maybe we are not able to create the right set of features. Neural networks might be a good tool for bypassing this issue of feature engineering. So indirectly, they can be used to give us a good representation for our problems. And in some communities, people usually call this unsupervised representation learning or feature learning. So this is it so far for today. And if you have questions, we can chat. I'm going to be here for a few minutes.
For your network, if each layer I use any
I didn't, sadly, I didn't specify, or I didn't have time to specify the whole model, but the idea is that, let's say, you represent each, you match each, somehow you need to represent words, right? How are we going to represent it? So one way of doing this is basically this. I'm going to have it become a lookup dictionary. And whenever I see words, I'm going to look up the words in my dictionary. It's a big one. And I'm going to do some transformation based on that. I'm going to basically, and so after that, my sentence, my sentence is just a vector, right? I'm going to map in this vector to some another space. And basically, I'm just going to try to map it into another. Now the training this model means that I'm going to perturb my vectors. Right? So the output of the system, this training, is going to be words and their vectors that hopefully are representative of their needs.
So with eventually repeating on the top of the
Something like that, but we need to be careful about how they're phrasing it. This is not one way of doing this. Oh yeah. So okay. Let me. Okay. So actually, for it to be forget about this. But think about the problem. Maybe that example was not good for this. I'm gonna take another example. I'm just creating a model. Even two sentences. How it goes. And I'm gonna look how phrasing it. The resulting characters of my model can be the vectors of verbs, can be good features with something like that, which involve verbs. But about this. This is mostly good. So let's say I want to learn a set of features. Let's say for example, I don't care about it. I give my input. If I expect to have a good set of parameters in my model, I expect the model to be able to reconstruct the input after doing some transformation. So I get input, I transform it, make some changes, and I try to reconstruct it. And the reconstruction should be as close as possible to it. And I minimize that error so that I get good weight for my parameters. Now I have a set of parameters which are tuned to different sets of inputs. I can use them as features. Oh, yeah, just one group one. It's working, self-mission for example.
Where shall we submit to the system?
I will tell you.
And another thing, we have another time for the determinant
If you cannot make it, you should email them with your reason. We will have time only if we have a justified reason, and you need to print it. It's not like we have it first. It's not like
in some classes. Yeah, we have exam.
we don't have makeup exam. We will have only if you cannot make the email exam for some certified exam. So if you have if you think you're gonna have problem, you need to okay. Problem?
Yeah, so like more of like so the wording in the book is really terrible. Like I
It is?
think like from my perspective, like
Like
so so I got this confusion with other ones like waiting for all only parameters or just all the number of mistakes you made and everything or anything else. Like this table is really confusing.
I think the person fixed it. There was a reading problem in the table. Like one of the tables was not just was not correct. They fixed it.
Other fixing?
They fixed it and announced it on Tuesday. Oh no. You just downloaded the table yesterday. Okay, so always try to use the latest version.
So I already like made like all the pretty much every
Compare your questions with the question on the website. And look at the tables.
because like I already figured out the whole table. Like I'm just like confused. Like I talked to one and
Okay, so in the worst case, you're just gonna update your key. It's not gonna be. It's not gonna change your algorithm.
right.
So if we announced it in the Fiesta, the hope was that you were gonna see, and they also announced it. They would announce it.
So like the whole whatever on the website right now should be potential problem.
Yeah. But if there is a problem, if there is a problem, just leave it. In case, any time that you see there is a problem,
Do you know like whether we should so what are we if it's not a table? Like every single one? Do we just fill out with parameters or do we fill out with parameters and mistake or anything else? Because I just fill out with all parameters.
without parameters,
With
all parameters.
all parameters.
Well, if you have all parameters,
That's fine. Don't have to include any like mistakes you made along with the cleaning or everything else.
yeah,
Or
I think
your project is not that deep.
uh,
The grader is not that deep.
unless you got graded, I might not be picky, but unless you got graded,